we're going to use double integral to calculate some relevant quantities that we usually see in the engineering and other applications. And one main topic we want to discuss by using this double integral is this is so-called the center mass for a laminar region or a plate region. Um, we want to introduce the definition and illustrate the calculation with some example. Okay, so let's look at the definition first. Suppose a laminar occupies a region D, and well, this you can think this is a two-dimensional object, and we want to smash it completely into one plate so that it does not occupy any thickness. When we talk about it, and this is definitely this ideal discussion, and we are just using this as the first approximation. All right, so the lambda region has this so-called density function, which is defined at any point x, y in the domain D. All right, and this symbol means it belongs to. All right, so the total mass of the lambda is then defined by this double integral of this density function over the entire domain D. So this is a pretty straightforward, right? And then we want to introduce two so-called the moment of the lambda about. So this is about the x-axis. Well, if you want to calculate the moment about the x-axis, you have to multiply this y to it. Okay, so moment about x, you want to multiply y to this density and compute the double integral. And on the other hand, if you want to compute the moment of the laminar region about the y-axis, which is defined given by this simple m sub y, you got to multiply x to this the density function and to the double integral. So the formula is pretty straightforward, right? And the use or the application of those formula in the concept we're describing is more important. So we want to introduce the concept of so-called the center of mass for this laminar region by using those two moments. Okay, so the center of mass x bar and the y bar will be given by the moment m sub y over the total mass of the laminar, little m, and so on and so forth. So with those two formulas, you got to remember those two formulas. All right. So now with these definition introduced, we can try to see if we are able to compute something. So let's look at this. So the density at any point on a semicircular laminar, I guess it's a half circle, right? Is proportional density. Remember, the keywords are the density proportional to the distance. Okay, what distance? The distance of a particular point, is any point, the distance from that point, xy, from the point to the center of the circle, right? So, by the way, how do we know the distance? So there's something we got to figure out. Distance between x, y, and the center of the circle. Well, here we use those x, y, and 0, 0. This implicitly, this sort of just assuming the fact that we already put our circle, our semicircle in a coordinate system, right? Because before we are writing down x, y, and 0, 0, we don't have to introduce the coordinate system because what the question is describing does not have a built-in coordinate system. It just say you have this lambda region, and at any point on this lambda, the density at that particular point is just proportional to the distance to the center of the circle. Because the center circle is a geometric quantity, it is fixed for the particular semicircular lambda region. All right, but here to actually facilitate the calculation and our discussion, we do introduce a coordinate system. And let me just draw it here. How do we do that? Okay. All right. So suppose we have R as the radius. So the semicircular region will look like this, right? And if we put the center of the semicircular region at the origin, then we have everything to be in this perfect symmetric arrangement. And this is what we usually like to do, right? So here, we overlap this semicircular region D with this coordinate system we're just introducing. And then we have one thing to continue our discussion with it, which is the density function. If you want to use this coordinate system to represent the density function, what do we do? Okay, so first of all, the density rho is a function depending on where you look at on this lambda region. Obviously, we are introducing this coordinate system, so rho of xy is a function. All right, so this function is what? This function is a proportional to the distance of that particular point to the center of the circle, right? So how do we compute the distance? Distance, well, d xy from the point xy to the center of the origin will be just this. The distance formula we learned before, and now the density is supposed to be proportional to this distance, and by using the mathematical formulation to formulate that description, is that we have the constant k multiplied with the distance. So this is how we define the density, and the k is a constant. We do not know exactly. K is constant. So in physics or engineering applications, in many situations, we will have to assume this, right? So now what? Now we almost get things done. So we want to find the center mass of lambda region because there are three formulas we need to compute this mass, total mass, the moment about x, and the moment about y. And then the moment about x and the moment about y will be used for the calculation of the center of mass, right? Okay, so we first calculate the total mass, which is the integration of a density function over the entire domain D. All right, so now what? Now this is obviously just the This domain D. How do we represent the domain D? Well, let me just write here. So the domain D here, obviously, is the upper half of this circle, right? So which is x squared plus y squared less than big R squared. Also, because we are only looking at the upper half, so we want to restrict our choice of y to make it bigger than 0. But this is a little bit awkward. Well, we'll see. We'll see how do we compute it. So now we have constant k times square root x squared plus y squared. And here we have dA, right? And then this is d. So if we want to write this in the iterated integral, what do we have to do? Well, we got to make sure we set up the boundary correctly. And here, because this circle over here is x squared plus y squared equals big R squared, we can solve for this y, right? It's R squared minus x squared, and we take the positive branch because we're only looking at the upper half of this circle. So now we can treat this as a type 1 region so that we integrate along this vertical stripe. All right, and then the clear iterative integral will be arranged. So the x is obviously from a negative r to positive r, right? So from negative r to positive r, and the y is going to start from 0 and stop at big R minus x squared, and k times x squared plus y squared, and we're integrating y first, and then x. So this is the iterative integral. But this obviously is not quite easy as we could think about, because there are too many square root. We don't like the integration have this square root, so we try to avoid that. So one way we can see is this look like a nice semicircular region. So how about we represent this by using polar coordinates? So in the polar coordinates, this domain D is going to be represented by r and theta. Okay, so r is what? Well, r is pretty easy. R is between 0 r is between 0 and big R. This big R is supposed to be a given number. And the theta is what? Theta is between 0 and pi. So we have this really nice, what do we call? We call this polar rectangle, right? This is a polar rectangle. So we would imagine if we convert this double integral into the polar coordinates, and then we will have the lower and upper bounds for both r and theta to be constant. So let's just do that. Compute or convert to polar using r and theta, right? So according to this and this, we can integrate either about r or theta first. That doesn't really matter. So how about we integrate about r in the interior, and then theta is for the exterior. So here we are assuming we are converting this dx dy or dA into dr d theta. But remember, in the conversion from dA to r dr d theta, we have to include this extra r. This r has to be included. So now we want to convert the integrand, which is k. Well, k is a constant. We can move it out. And square root x squared plus y squared is what? Remember, r equals square root x squared plus y squared. So this is r. The integrand is just r itself. Now we have everything settled. Now we have to determine the lower and upper bound for theta. We already know it's from 0 to pi. And for r is from 0 to big R. So this is what we have. And now you can see this is much easier calculation. And we have the integrand r squared. So the antiderivative is becoming r cubed over 3. So this is what we have. All right, and then we see so it's constant k times 0 to pi. Now we have big R cubed over 3 d theta. All right, and then this is becoming constant k big R cubed over 3 theta, for theta equals 0 to pi. So this is k R cubed over 3 pi. So this is the total mass of this laminar region. Okay, so this looks much better, right? Compared to the double integral formulated in the Cartesian coordinates. All right, so it's a similar calculation we can do to get this moment. Remember the x moment, which is the moment about x-axis is m sub x, and m sub y is the moment about the y-axis, and here we're multiplying. Well, let's not change the order. Over here, m sub x is the moment for the laminar region about the x-axis, is multiplying y to the density function. And then we compute this because this will be used in the second coordinate of the center of mass. We have to remember. Let me just write it down. The center of mass is what? The center of mass is my over m, capital Mx over n. Let's see. Yeah. Okay. Well, if you don't remember this, whatever you multiply in the integrand is used for that particular coordinate in the center of mass. You should remember that. Okay. And then capital My, this is, and those are the calculations we need to carry out. And obviously, we still remember the domain D is a polar rectangle, so it's better for us to write them into the polar coordinates. And so we don't have to use the Cartesian coordinates. So let's just use the polar coordinates directly. The first one. So theta is between 0 and pi. And r is between 0 and big R. And here, remember, we're computing this first. So what is y? Y is r times sine theta. X is r times cosine theta. We have to remember that. R times sine theta times k times r. And remember here, dA is r times dr d theta. This has to be remembered exactly. So r times dr d theta. Remember this piece, this k times r is the integrand of the density function. All right, and then here is y is r times sine theta. So the three pieces are translated into polar coordinate exactly. All right, so now let's look at this. So we have r squared actually r cubed. R cubed, the antiderivative about for r cubed about r is r to the 4 over 4, right? And then there's k, we move the k out, and then there's a sine theta multiply. So we have little r is at 0 for big R. So this is what we have for the first part of calculation for the interior integral. So now we have this is sine theta times r to the 4, so big R to the 4 over 4 minus 0 d theta. And remember, the the antiderivative for sine theta is, I think, is a negative cosine, right? So here we have k times big R to the 4 over 4 times negative cosine theta as the antiderivative. And then we keep going. So we have constant k times r to the 4 over 4. And then we have negative cosine pi minus negative cosine 0. So this is what we have. So we have neg k times r to the 4 over 4 multiply, what is this is? Cosine pi is negative 1. Is that right? So cosine pi is negative 1. So we have negative 1 is positive 1 minus cosine 0 is 1. So this is what we have in the bracket. Oh, so it's becoming 2, right? So this is k times r to the 4 over 2. Okay. And then now what is moment about the y-axis? So this is according to your calculation. Let's just copy it down here. And then we can convert it into polar coordinates. Right, so theta and r. And now let's use the same color. This is x. We're going to write x in polar coordinates, which is r times cosine theta. We're going to write this density function into the polar coordinates also, which is k times r. And then finally, differential area is r times dr d theta. So now we have the r is between 0 and the big R, theta is between 0 and the pi, and then we have everything we need to finish the calculation, right? So r cubed, the antiderivative, we can move this k out first. Okay, and then we find the antiderivative. Well, there's a cosine theta, we can write it out first. Antiderivative for r cubed, which is r to the 4 over 4, and the little r is at 0, and the big R theta. So this is becoming k times this integral for theta, cosine theta, big R to the 4 over 4 minus 0. We can ignore it. And then we integrate about theta. So cosine theta is having the antiderivative of sine theta. So sine theta. And then we have constant k and r to the 4 over 4. This is what I have. So we have constant k r to the 4 over 4. What is the sine theta at pi? No, I think it's 0. What is sine theta at 0? Well, sine 0 is 0. So this is a, for here, it's 0 minus 0. So the result is 0. Okay, so now we can compute the center of mass. The center of mass is indeed, okay, so this is supposed to be 0 over, what is the center, what is the mass? M? Yes, this is M. M is K. Remember, M is K times R cubed over 3 times pi, right? K R cubed over 3 times pi. And this is K R to the 4 over 2 divided by the mass. And this is what I have. Obviously, this is center mass is indeed 0. So K is cancelled. And we have R in the numerator. And then 3 divided by pi. This is the center mass for any laminar region that has a density function that is, which is proportional to the distance from the point to the center of the circle.